Hello friends, welcome back to my channel Chemistry Unplugged. So today we will take substitution reaction in octahedral complexes. There are three different type of mechanisms to define substitution reactions in octahedral complexes: dissociative, associative and interchange mechanism. So we will take all three of them. What are the type of intermediate form in these mechanisms and what are their concept? So we will also take most of the octahedral substitution reaction takes place through dissociative mechanism. So we will take different evidences to support dissociative mechanism of octahedral complexes, and these evidences are water exchange and most important is acid-base hydrolysis. And we will take its mechanism and what are the important key points which has been asked in the examination. We will also take questions from CSI and Net and Gate based on this topic. So you can follow me on Unacademy using my name or this link where I am continuously uploading lessons on organic chemistry. So you can follow me there also. And please subscribe to my channel and click on bell icon for future notification. So let's start the video. So most of the reactions in octahedral complexes are due to the substitution reaction. So substitution reaction, and among substitution reaction, the most important type and the most important reaction is nucleophilic substitution reaction. Suppose we have a complex like this, Ml5, and here we have a ligand, different ligand X, suppose. And we are using another ligand to replace it. And in this complex, this L is inert ligand and X is labile ligand, means it can be easily replaced by Y. And Y is the incoming ligand. So this will be the final product of this reaction. X is replaced by Y. Okay, so because ligands have either a lone pair of electron or they have negative charge, so they are acting as a nucleophile. That is why most of the substitution reaction in octahedral complexes are of substitution nucleophilic type. So we have three mechanisms to explain these substitution reaction. First is dissociative mechanism, second is associative mechanism, third is interchange mechanism. So first we will take dissociative mechanism. Dissociative mechanism means, suppose we have a complex like this, and I want to replace this labile ligand with a ligand Y. So in dissociative mechanism, the first step is the removal of X and we get an intermediate of 5 coordination number. This is an octahedral complex which has 6 coordination number, but in this step, this step is slow and this step involves removal of X. And we get a intermediate of coordination number 5. So there is the decrease in the coordination number of the complex. And next step is the addition of Y. This step is fast and we get a complex like this, Ml5Y. So again here L is inert ligand, X is labile ligand and Y is incoming ligand. So you get a complex of, you get an intermediate with low coordination number. Okay, and second important thing is, first there is MX bond break. This MX bond is completely break and then we get an intermediate with low coordination number, then a new bond will form. So there is complete breaking of bond in this mechanism. This mechanism is of first order because this involves only one species and this step is slow step. This is rate determining step. That is why it is first order substitution nucleophilic reaction. So we can write it like SN1. And the rate of reaction depends on the concentration of this complex because this is the rate determining step. Then we get a complex intermediate of coordination number 5 and this intermediate can have two different type of geometries. It can have trigonal bipyramidal or it can have a square pyramidal intermediate. square pyramidal shape. So in trigonal bipyramidal shape, the shape can be like this, and in square planar, in square pyramidal, the shape will be okay. So two different type of geometries of intermediate in this mechanism. Next we will take associative mechanism. In associative mechanism, suppose again we have the same complex Ml5X. So in this mechanism, the first step is the addition of Y. So it will give us an intermediate of higher coordination number. Its coordination number is 7. And this step is slow step, again rate determining step. The next step is fast, which involves removal of X. So we have our final product Ml5Y. This intermediate has coordination number 7. So it can have two different type of geometries. First is pentagonal bipyramid. Like this. This is pentagonal bipyramid. Second possibility of geometry is octahedral monocapped. Next mechanism is interchange mechanism. This mechanism involves formation of activated complex. Means suppose we again have a complex like Ml5X. So it involves an activated complex or a transition state. There is no intermediate in this reaction and we have a transition state. Means there is simultaneous attachment and breakage of MX bond and MY bond. Simultaneous breaking of MX bond and attachment of MY bond. So situation is like this. This is a transition state, not intermediate, it is a transition state. And this interchange mechanism can be of two type. We can have interchange dissociative mechanism, which is denoted by ID, and we can have interchange associative mechanism, which is denoted by IA. Next we take evidences in favor of dissociative mechanism. Most of the substitution nucleophilic reactions in octahedral complexes are of dissociative type. We need some evidences to support that most of the reactions are of dissociative mechanism. So first important evidence is water exchange process. Suppose we have aqua complex of chromium like this, and we are using isotope of water, different isotope of water to exchange this water ligand. So using this process we can find out that mechanism is following dissociative mechanism. This reaction is following dissociative mechanism. Next important thing is the water exchange process depends on the charge density of complex. This water exchange process depends on the charge density of metal in the complex, and the charge density is equal to charge upon size. So as the charge increases, charge density increases, or the water exchange or the strength between metal and this is directly proportional to the bond strength of metal with water. It is directly proportional to this bond strength. So as the charge density increases, MOH2 bond strength increases. So when we will go down the group, size increases but charge remains same. So charge density decreases. In this way, this MOH2 bond strength also decreases. Bond strength also decreases. Okay, next we have the most important thing in this process, in the water exchange, the order of water exchange. we have an order of metal ion which can easily exchange water. This series is like this. Highest for copper plus 2, then chromium plus 2, zinc plus 2, manganese plus 2, iron plus 2, nickel plus 2, and least for the vanadium plus 2. And dipositive metals have higher tendency to exchange water than tripositive. So this is the order for tripositive metal ions. And the next important thing is the rate of water exchange for alkali and alkali earth metals is also very high. Means it is high for copper plus 2, but this water exchange is also very high for alkali and alkali earth metal, except beryllium plus 2 and magnesium plus 2. These are two exceptions. Except these two, other alkali and alkali earth metals have higher rate of water exchange. So you have to remember this water exchange order, and it has been asked in the examination that they will give you certain metal ions and then they will ask you which among the following will show highest rate of water exchange. We will discuss a question from CSI and NET like this, and here and there we will use this series. So remember this series, and always remember this, the dipositive metal ions have higher rate of water exchange as compared to tripositive. Next we will take anation reaction. Anation reactions are also the proof of dissociative mechanism, and these reactions are replacement of water by anion. Suppose we have an example of aqua complex of nickel and we are exchanging water molecules by an anion. So this will be the complex. And in this reaction, the rate determining step is the breaking of nickel water bond. Means there is a formation of intermediate with coordination number 5. It means it is following dissociative mechanism. Next evidence is the equation or hydrolysis reaction. It is the most important evidence, and equation or hydrolysis means replacement of ligand with water molecule. Replacement of ligand by water molecule. The hydrolysis can be of two types: acidic hydrolysis and basic hydrolysis. When we are carrying out hydrolysis in presence of acid, then it will become acidic hydrolysis, and in presence of basic medium it will become basic hydrolysis. In acidic hydrolysis, the ligand is replaced by water molecule, and in basic hydrolysis, ligand is replaced by OH ion. This is the basic difference between two types of hydrolysis. In acidic hydrolysis, ligand is replaced by water molecule, and in basic hydrolysis, ligand is replaced by OH ion. So first we will take acidic hydrolysis. Acidic hydrolysis means replacement of ligand by water molecule. So we will take an example, and this example is very important. It is cobalt third amine complex. So we are taking this complex. So in this complex, when we are using water in presence of acid, then this X ligand, which is labile in nature, will be replaced by water. This X can be fluoride, chloride, iodide, and NCS minus, nitrate. So we have certain evidences which can support that most of the acidic hydrolysis are of dissociative type. Okay, and so first we will take nature of leaving group. Suppose we have different types of X and we are placing different atoms of halide here. Suppose we have fluoride, chloride and bromide, iodide. So these are the leaving groups FCl, Br and I. And if we are going from left to right, the bond strength decreases. So it is easy to replace this cobalt iodine as compared to fluoride from this cobalt. So iodide is a better leaving group. So this will be the order of rate of hydrolysis. Okay. So as the metal ligand bond strength increases, it is difficult to break that bond, difficult to remove the ligand, and in this way the rate of reaction is decreases. So as the bond strength increases, rate of reaction of acidic hydrolysis decreases. Okay, so here we have a order of different type of leaving groups for cobalt third amine complex. Lowest is the bond strength for nitrate, so it is the best leaving group. The rate of reaction is highest for nitrate when leaving group, then iodide, Br minus, Cl minus, fluoride, and then NCS minus. So this is the order of leaving groups, and the rate of reaction is highest for this. Rate of acidic hydrolysis. Rate of hydrolysis is highest for this and lowest for this. Okay. Then we will take second evidence, which is known as charge effect. Charge effect means as the charge on complex increases, the rate of hydrolysis decreases. We have already discussed in the stability of the complexes that charge effect increases the stability of complexes. So when the stability increases, their water exchange or the hydrolysis process decreases. Their substitution reaction rate will decrease. For example, we have a complex of cobalt. So in this complex, the complex has +2 charge and this complex has +1 charge. The rate coefficient, the rate constant for this reaction is 6.7 10 to the power minus 6 second inverse, and for this reaction it is 1.8 10 to the power minus 3 second inverse. So this reaction is much faster than this one. So as the charge increases, rate of reaction, rate of acidic hydrolysis decreases. Next we will take effect of chelation. So suppose we have two type of complexes of cobalt. This is the complex in which we have 5 ammonia ligand and 1 Cl. In this we have ethylene diamine which can show chelation. And the charge on both the complexes are same, so there is no charge effect. So here we will consider the effect of chelation. So in this complex, suppose it is following dissociative mechanism, so it will give us an intermediate of this type, which has a coordination number 5. This will be the intermediate. Okay, and in this case, we will have an intermediate of this type. Okay, so in this complex, it is easy for the incoming ligand, that is water molecule, to approach central metal atom. Okay, but in this case it is difficult for the incoming ligand, that is water molecule, to approach central metal atom because of the presence of this chelating ligand. Because of its larger nature, it is difficult for the water molecule to approach this central metal ion. So the rate of reaction for this complex is low. Suppose this is the 1 and this is second. So for the second, the rate is very low as compared to 1. It means it is following the dissociative mechanism, because in the dissociative mechanism we will have 5 coordination number, and in case of 5 coordination number, this smaller size intermediate will attract incoming ligand, that is water molecule, and this larger size intermediate will hinder the approach of incoming ligand. Okay, so the effect of chelation decreases the rate of acidic hydrolysis. Then we have effect of steric hindrance. Steric hindrance increases the rate of acidic hydrolysis. So remember this, steric hindrance increases the rate of acidic hydrolysis, which is following acidic hydrolysis or any type of hydrolysis, because all of them follow dissociative mechanism. If it is following associative mechanism, then in case of associative mechanism we have an intermediate with +7 coordination number, and steric hindrance will decrease the rate of reaction in case of associative mechanism because of the larger coordination number of metal ion in the intermediate. But in case of dissociative mechanism, because we have a intermediate of coordination number 5, so the rate of reaction increases with increase in steric hindrance. Then we will take base hydrolysis. So suppose we are using this complex of cobalt. Cobalt is in +3 state again, and we are using base hydrolysis. So we will use OH minus, a conjugate base like this, because it is acting as a acid and you will get a conjugate base. This OH minus will remove one H from the one of the NH3. So you will get an intermediate or a conjugate base like this. I will write it like CB, conjugate base. Then next step is slowest step, and it is our rate determining step. So I will write it KB, it is the coefficient for this hydrolysis, and you will get an intermediate with coordination number 5. So again it is following dissociative mechanism in which coordination number decreases. The next step is again fast. It is attack of water molecule and you will get your final product. So finally there is attachment of OH minus after the basic hydrolysis. So the basic hydrolysis involves SN1CB mechanism. What is its mean? Substitution nucleophilic unimolecular conjugate base mechanism. All the hydrolysis, acidic or basic, involve SN1 mechanism, dissociative mechanism, and CB means it involves formation of conjugate base. So it is following SN1CB mechanism. This is very important. Next important thing is the rate of base hydrolysis is much faster than acidic hydrolysis. This is very important. And the reason of the high rate of basic hydrolysis is, first is KB is much higher than Ka. Rate coefficient for basic hydrolysis is much higher than acidic hydrolysis. Then amido complex has less charge. Amido complex means this conjugate base intermediate has less charge. Less charge means it is following charge effect, and when we have less charge, then the rate of reaction will be fast as compared to the starting complex which has +2 charge. This conjugate base has less charge and it is participating in rate determining step rather than this one. So In this starting we have higher charge, but the species which is involving in rate determining step has less charge. Okay, in case of acidic hydrolysis, you are directly using this complex which has +2 charge, but in case of basic hydrolysis, this conjugate base is participating in the reaction rate determining step and it has less charge. This is the second region of higher rate of basic hydrolysis. Then next region is NH2 stabilizes intermediate. The NH2 in this intermediate, this is the intermediate, and in this intermediate, this NH2 is stabilizing the overall intermediate. How can it stabilize? Suppose we have this cobalt and it has bonding with NH2. Okay, so in this NH2, nitrogen has a lone pair of electron, so it can donate its electron to the cobalt. Okay, and we have pi bonding here. There is pi bond formation by donation of electron by cobalt. So this pi bond increases the charge density around the cobalt. It increases charge density. Charge density means increase in the electron cloud around cobalt. And when it has higher negative charge, it can easily repel the labile ligand. And the second region is this pi bond formation. There is formation of a pi bond like this. So due to the formation of this pi bond, this intermediate will become stable. Okay. So when the intermediate is stable, then the rate will be fast because it is formed in the rate determining step. So these are the three important reasons why basic rate of basic hydrolysis is faster than acidic hydrolysis. Then we will take some key points about basic hydrolysis which are very important and will help you to solve many questions. First point is OH abstracts proton from ammonia group which is trans to leaving group. What is its mean? So in CO NH3 Cl complex, this is the situation. Okay, so in the basic hydrolysis, the ammonia group which is trans to leaving group, we have this as a leaving group and this ammonia is trans to this leaving group. So hydrogen will be abstracted, proton will be abstracted from this ammonia. So we have this one. Okay, and in next step Cl minus will be removed and then water will attack on the intermediate. So always remember that OH abstract proton from ammonia which is trans to leaving group. Next important point is presence of pi donor ligands. Pi donor ligands like, so example of pi donor ligands are Cl minus, Br minus, I minus, then NH2, NCS. Which ligand has lone pair of electron to donate to the central metal ion. So these are the type of pi donor ligand, and in presence of pi donor ligand, there is formation of trigonal bipyramidal as an intermediate. The shape of intermediate will be trigonal bipyramidal. We have discussed that in case of dissociative mechanism, we have two type of intermediate. Either we can have trigonal bipyramidal or we can have square pyramidal. And when we have pi donor ligands, then formation of trigonal pyramidal intermediate is favorable. Okay, and in absence of pi donor ligand, square pyramidal intermediate formation is favorable. Okay, so this is the second important point. And then third point is, it is essential to have at least one ligand with acidic proton. It is essential that our ligand have at least one acidic proton which can be removed by using OH minus. So suppose we have these complexes. So these complexes do not have any ligand which have acidic proton. There is no proton in these ligand. So there is no effect, or they are independent of OH concentration. They are independent of OH concentration because they don't have any acidic proton. Then fourth point is basic hydrolysis also follows dissociative mechanism. Then we will take an example here. Then we have here three complexes of cobalt. All of them have same charge. And they ask you to find out which has highest rate of basic hydrolysis. So in case of this complex, all these complexes have pi donor ligands because they have ethylene diamine, so it can donate to the central metal ion to form a pi bond. But in case of this ligand, we have nitro group, and this nitro group have a tendency to attract electron towards it. So it will attract electrons donated by, so it will attract electron towards it. So in this way, the charge density around cobalt will decrease in this case. It will also decrease in this case because we have cyanide group here which also has electron withdrawing character. But the attraction or the withdrawal will be highest in case of nitro group, or the charge density is lowest in this complex. So the rate will be lowest for this one. And this complex doesn't have any molecule or the ligand which can attract electron or can reduce electron density. Okay, so this has highest rate than this one and lowest for this one. So next we have an example of cobalt complex. It has a ligand tris 2-amino-ethyl amine group which is also denoted by tren. Tren is tetradentate ligand. Okay, and this complex can exist in two forms. It can have two type of isomers. So this isomer is red in color, which is also known as red isomer, and this one is purple isomer. Okay, then if you do the basic hydrolysis of this complex, then it has group which has acidic hydrogen. Suppose it is the leaving group. Cl is leaving group, and this leaving group has a group at its trans position which can donate proton. So it can has replaceable hydrogens. But if you look at purple isomer, then in case of purple isomer, the leaving group is Cl again, and it has nitrogen as trans group which doesn't have any acidic proton. So it cannot easily donate proton. And we know that in case of basic hydrolysis, we know acidic hydrogen trans to leaving group. Okay, so rate will be fast when we have acidic protons trans to leaving group. So its rate will be high. So the rate will be high. I can denote it like this. The rate for the red isomer will be higher than purple isomer. Then second important thing is, because tren is the ligand which has lone pair of electron or nitrogens, so it can show pi bonding. So it is a pi donor ligand. Pi donor ligand means it will stabilize, it will form trigonal bipyramidal as a intermediate. The geometry of intermediate will be trigonal bipyramidal. And if you do hydrolysis of red isomer, which rate is higher, then it will show complete retention of configuration. Means you will get the product like this. 100% product will be like this, in which you have OH group in place of Cl. The structure will be like this. This will be the structure, and you will get 100% of this product. And in case of purple isomer, in which leaving group, in the transposition of leaving group does not have any acidic hydrogen, so this or this nitrogen will donate its proton, and you will get a mixture of product. You will get 85% of product like red isomer and 15% of product like purple isomer. Means in case of 85% of product, OH will be in this position, and in case of 15% of product, OH will be in place of Cl. So now we will take questions from CSI and NET. First question is from December 2018. So this question is similar to the previous example which we have discussed, and this is similar to the red isomer and it is purple isomer. So in this case we have acidic proton which are trans to leaving group, and in this isomer we do not have any proton trans to leaving group. The question is the isomer A, this is isomer A, and isomer B undergoes base hydrolysis by forming a trigonal pyramidal intermediate. The correct statement is A reacts faster than B and both give mixture of product. B reacts faster than A and both give mixture of product. A reacts faster than B and B gives mixture of product. Fourth option is B reacts faster than A and A gives mixture of product. So we know that A isomer, which is red isomer, in which we have protons trans to leaving group, will show faster rate of reaction than B isomer. Okay, and A isomer show complete retention of configuration, and we get 100% of product like red isomer. And in case of B isomer, we get a mixture of product. So the correct answer will be A reacts faster than B and B gives mixture of product. So this answer will be correct. Third option. The next question is from June 2017. The relative rate of water exchange for hydrated complex of nickel plus 2, vanadium plus 2 and Cr plus 3 ions will follow the trend. I have told you in the water exchange application that you have to remember a certain series, and using that series we can determine the rate of water exchange process. And there I have told you that dye-positive ions, metal ions, show faster rate of reaction as compared to tri-positive ion. So the options are these four, and you have to find out the correct option. So if you remember that series in which Cr plus 3 has the lowest rate of water exchange, so C will be at the least end. Then among nickel plus 2 and vanadium plus 2, nickel plus 2 has higher rate. So C has the lowest rate, and then B, and highest is the rate for A. If you look at the series, then you will get this answer. Next question is from June 2018. Consider the following statements. First is chromium plus 2 is easier to oxidize than vanadium plus 2 in gas phase. Chromium plus 2 in aqueous phase is more powerful reducing agent than vanadium plus 2 in aqueous phase. And the third statement is the rate of water exchange for chromium plus 2 aqueous in aqueous state is much faster than vanadium plus 2 in aqueous phase. So the correct statements are A and B, A and C, B and C, and ABC all. So the first statement is chromium plus 2 is easier to oxidize than vanadium plus 2 in gas phase. So it is the wrong answer. In aqueous phase, Cr plus 2 is more powerful reducing agent. We know this. B is correct. And the rate of water exchange of Cr plus 2 is much faster than vanadium plus 2. So if you look at the series of water exchange rate, then you can find out that Cr plus 2 rate is much faster than vanadium plus 2. So C will be the correct answer. So B and C are the correct answer. The option 3 will be correct. Next question is from December 2017. The question is, consider the following statement with respect to the base hydrolysis of this cobalt complex to this one. First is, one of the ammonia ligand act as a Bronsted acid. Second statement is, the entering group is water. A hepatocoordinated cobalt plus 3 species is intermediated. Then correct statements are A and B, A and C, B and C, and C only. C is the wrong statement because it follows dissociative mechanism which involves formation of intermediate with coordination number 5. So it cannot be hepatocoordinated, which means 7 coordinated. So this is the wrong statement. Entering group is water is the correct. Then one of the ammonia ligand acts as a Bronsted acid. It is also correct. So A and B are correct. So the first option will be the correct answer. So that's it. I will end my today's video here. Thank you so much for watching my videos. Please subscribe to my channel and click on bell icon for future notification. In next video, I will tell you about trans effect and mechanism in square planar complexes. So keep watching. Thank you.